ubiquitous hardboard, which is spread into the glass or onto ceramic, and you do that to analyze microstructure, if you want to know about something about the texture, or if you want to calculate the fracture toughness, or if you want to analyze the quality of the circuit. That are the three main points for why it's done. And when you push it, and then you induce stresses, and the component in the radial direction is tensile only in certain region below the surface, and it's always outside the contact radius with the ball. So the crack, if it should fulfill the couplet criterion, it should probably be initiating in this region. When we look in the direction of the force, which pushes on the ball, then from the top we will see a ring crack which initiates. But when we do cut through and look in the cross section, we will see that this ring at the surface then extends to the top. So, and I will motivate our simulation by experience from the past, because it started in 1891. It's quite old stuff. The first observation was that the critical force which causes this ring crack is linearly dependent on the ball radius. And if we take the Hertzian theory of contact, and we take the equation for the maximum radial stresses, which is at the contact radius at the surface, and we say the material properties are the same, Poisson ratio is the same, and then we know that this ratio is constant, it is empirically observed, then in the equation there remains ball radius. That means the strength is, it's a paradox, it's not a material property, but it's a function of the ball radius, function of the indentation, which doesn't make sense. If it was function of the square of the ball radius, then everything would be constant and strength would be like material property which is constant. And 50 years later, Tillet did experiments with bigger balls and noticed that this region of linear dependence ends at certain ball size, and from that, with bigger balls, the region or the regime completely changes. And this dependence on the square of the ball radius starts to make sense. But how to explain it? People also did experiments with etching of the surface and noticed that when you etch the surface of the glass, you probably increase the quality, you get rid of the defects, and the fracture forces get higher, and this switch of the regions gets into the region of small balls. Another important observation was by Možinov and August. They noticed when they polish surface with the silicon carbide paper, they get completely linear behavior, but when they take the diamond paste and polish it, it completely changes the regime in the whole region of ball sizes and becomes quadratic. So, then people started doing indentation of ceramics. It was done on the silicon carbide. Then at the Institute of Structural and Functional Ceramics in Melbourne, they did indentation into alumina and observed this linear behavior, and indentation of silicon nitride, where there was approximately this quadratic behavior. So questions from these observations are: why this force sometimes depends on the ball radius linearly and sometimes quadratic? Or in other words, why the maximum radial stress, which is equal to the first principal stress, why it's sometimes constant and sometimes it is a function of the ball radius? And can be explained by the strength or flow statistics, or do we need to use linear elastic fracture mechanics, or can the couplet criterion explain it? And how do we take into account the surface quality? And why these ring cracks always initiate at certain distance outside of the contact radius? It's never exactly at the contact radius where the stresses are the biggest. And what is the role of friction? So people were modeling that for 70 years almost. And original complaint was that the Weibull statistics or the flow statistics is not usable because on one hand, you would observe with smaller bores, bigger scattered in forces, relative, because you have smaller area where you need to find defects, so it would be harder to find this. Second objection is your effective volume or effective area is also depending on the bore radius, so how do you use it? Third objection is that your Weibull modulus should be the same, the slope of the Weibull modulus should be indicated between different sets of experiments, and that was not observed. So people took analytic expression of the subsurface radial stresses and integrated over that to calculate stress intensity factors, and they did it for the different locations, and then try to take into account the kink in the shape of the crack, and etc. etc. And the most cited model is by this Italian law, and they have a model which fits the data perfectly. However, you need to have the experience first. You need to assume that your crack will first grow stably, then it stops, and it will continue. Plus, you have two constants which you just need to fit. So for us, it's not as good because we need to introduce different new material properties, and we don't want that. And also, we cannot say anything about the location of the crack. So we revived the issue with finite fracture mechanics, which was explained in the plenary lecture. And we are not the first who uses this problem. Last year, there was a guy called Han, and he took this analytical expression of stress field, and again calculated the A1, recalculated to the energy release rate, then integrated with the incremental energy release rate. And then he has this field which you can analyze. We started with the numerical methods directly with the finite element method because we want to play with the friction. We want to analyze if the 3D makes sense, or we can simplify it into axis symmetry, or we even try to replace the contact, which is nonlinear, with a pressure distribution, which makes the calculation much faster. So I will show you how the results look, and I will indicate on horizontal axis relative position to the contact radius, which is at the number 1, and this is outside the contact radius. And on the vertical axis are normalized fracture forces, and the region signifies where the couplet criterion is fulfilled. The red means the stress is fulfilled there, but not the energy one. The yellow one is the opposite, and the red one, neither the stress nor the energy criterion is fulfilled. So we took the experiments from Pillet, and we get no match. We predict half of the forces, so probably not working yet. Then we took the experiments with working silicate glass. Here we have somewhat match, but not really. Then diamond with the silicon carbide, I would say no match. Tungsten carbide with alumina, no match. Tungsten carbide with silicon nitride, again failure. So it's probably wrong. So we need to check what the initial shape assumption is, if the axial symmetry is actually correct, and if we can replace the contact with pressure, and what is the reason of friction. We can go into that in discussion, but I can tell you now, neither of these will help you to solve the problem. So if you compare the full 3D contact modeling with friction and the analytical solution, you get basically the same forces. And then I looked into the publication of Han, and his explanation was, let's just increase the fracture toughness by 2 and make the strength of the glass instead of 90 almost 800, which is not acceptable for us. So maybe we don't see the whole picture, and we need to get more experiments. One critical experiment is from the weight, which had silicon carbide, which was annealed at 2000 degrees. And the other critical information is from the work of Raul and Ševeček, who try to look at the different surface quality with grinding, polishing, different grain sizes. And then, this is for one ball size. On the left side, this is grinded, polished, and polished very finely. No difference in the surface quality. When he annealed this middle set in 1000 degrees, again nothing. But then when he annealed that in vacuum at approximately, I guess 1400 or 1600, now suddenly the forces drop. So that should be indicator what's happening and what we are missing. Then we found the measurement of residual stresses at the surface, and in the case of silicon nitride, the surface is experience approximately 1 to 3 gigapascals of compressive residual stresses, but that stress decays very rapidly, and it's approximately in the first or second layer due to the polishing and the forming of the grains. However, in this case, it's very significant, and we need to include it. So when we model without residual stresses display, which was annealed, we get almost perfect match with the experiments. Then with the annealed experiments from Papšík cohort, again I would say here the coupled criterion is not fulfilled at the same time, but if we take the not absolutely the strength criterion from the surface to the depth everywhere, but we approximate, then this blue region would fit it perfectly also here in the topic. And if we want to get these non-annealed data, we just need to introduce residual stresses, which will approximately fit the data. The same with the glass, and we across the different ball sizes match. Here it doesn't fulfill the coupled criterion, but it seems that the incremental energy criterion is enough, and for some reason it just makes sense with comparison with the experiments. The same with this borosilicate glass. We get the second regime, as you remember, it was linear or quadratic. With diamond silicon carbide, again almost perfect match. With alumina, the same. Silicon nitride, the same. Probably we just cannot ignore in some cases the residual stresses, and we need to include them into the model. And using this coupled criterion, we can explain why it's not at the contact radius exactly, because the force required to initiate there will be much higher than some optimal minimum farther from the contact radius. If we do not have the measurement of the residual stresses, we can use different ball sizes, get the critical forces, then try to match the residual stresses which would make sense, and we can compare later with the experiments. So it is hypothesis, the residual stresses are causing that, but it is a hypothesis which can be disputed, so we can work with it. Yeah, so that's the story, that the residual stresses are the issue, and I would like to thank my colleagues and friends, and also the ECR for providing us with financial. Any questions?
Thank you very much. So I would like to ask a question. So it's a hypothesis, right? You know, someone would say, okay, increase the K on C, maybe that's the wrong thing. The other one would say, okay, we have to cover the residual stresses. The thing is that the residual stresses for each one you have to adapt them. It's not something which is the same value, right? So sometimes it's 0, sometimes it's that number, and you have to play with the numbers in order to match the results.
If I know the data from the literature, that's for alumina, we have it. Silicon nitride, we have it. So I did not have to match the residual stresses to fit the data. I just took what is in the literature, and it was working.
So you look in the literature on what are the residual stresses that would be there, and then you apply that and then it match.
There are experiments where people try to compare what is the residual stresses when you polish it, when you grind it, transverse direction, longitudinal direction. So data are there, and we can use this data to predict the.
Is there a way so that you can measure what are residual stresses on the surface and take that into consideration?
I'm not an experimentalist, but I was told that you can measure that with XRD or synchrotron, but I don't know the accuracy of these measurements.